Hello you all, welcome all my students. Now let me go to the next question in this series on solutions to JEE Main 2018 Physics. Before going further, please do press the subscribe button and don't forget to press the bell icon to get the notifications of all my future videos. My next question is, a telephonic communication service is working at a carrier frequency of 10 GHz. Only 10% of it is utilized for transmission. How many telephonic channels can be transmitted simultaneously if each channel requires a frequency of 5 kHz? The choices are 2 into 10 raised to power 6, 2 into 10 raised to power 3, 2 into 10 raised to power 4 and 2 into 10 raised to power 5. Now that's a very simple question from communication systems. It's given that the telephonic communication service is operating at a carrier frequency of 10 GHz, that is equal to 10 into 10 raised to power 9 Hz. Since only 10% of it is utilized for transmission, therefore the available bandwidth is 0.1 into 10 into 10 raised to power 9, which is equal to 10 raised to power 9 Hz. Since each telephonic channel requires a bandwidth of 5 kHz, therefore the total number of channels n that can be communicated simultaneously is equal to available bandwidth divided by bandwidth per channel, which gives me 10 raised to power 9 divided by 5 into 10 to the power 3, which works out to be 2 into 10 to the power 5 channels. Oh nice, we have got the answer. This was a very simple question. You can see for yourself that our answer matches with the fourth choice. Therefore the fourth choice is the right answer. Our next question is, a granite rod of 60 cm length is clamped at the middle point and is set into longitudinal vibrations. The density of the granite rod is 2.7 into 10 to the power 3 kg per meter cube and its Young's modulus is 9.27 into 10 raised to the power 10 pascals. What will be the fundamental frequency of its longitudinal vibrations? The choices are 7.5 kHz, 5 kHz, 2.5 kHz and 10 kHz. Let's try to understand the question. This is a very simple question from standing waves. Before we go any further, let's watch this short video clip on standing waves. We know that the speed of longitudinal waves, c, is equal to root of y divided by rho, where y is the Young's modulus and rho be the density of the material. Or c is equal to root of 9.27 into 10 raised to the power 10 divided by 2.7 into 10 to the power 3, which on calculations give me 5.86 into 10 raised to the power 3 meters per second. In the given problem, the rod is clamped at the middle, therefore the middle point should be a node, whereas the two ends are free to vibrate and must therefore be antinodes. So in the fundamental mode of vibration, L is equal to lambda by 2 or lambda is equal to 2L or lambda is equal to 1.2 meters. Now the fundamental frequency nu f is equal to c divided by lambda or is equal to 5.86 into 10 to the power 3 divided by 1.2, which on simplification gives me 4.88 into 10 to the power 3 Hertz, which is closest to 5 kHz, and my answer matches with the second choice of the given choices. My next question is, it is found that when a neutron suffers an elastic collinear collision with a deuterium at rest, the fractional loss of its energy is Pd, while for its similar collision with carbon nucleus. The fractional loss of energy is Pc. The values of Pd and Pc respectively are. The choices are 0,1, 0.89 and 0.28, 0.28 and 0.89 and 0,0. This is a very simple question from momentum and collisions. We know that all collisions involving fundamental particles are elastic in nature, and for head-on elastic collisions, the velocities v1 and v2 of the two particles when m2 is at rest are given by v1 is equal to m1 minus m2 divided by m1 plus m2 into u1, and v2 is equal to twice of m1 divided by m1 plus m2 into u1. Or the practical manifestation of these two equations is shown in the following video clip. Now, in an elastic collision, the kinetic energy lost by the first particle is exactly equal to the kinetic energy gained by the second particle. Therefore, Pd is equal to half m2 v2 square divided by half m1 u1 square, where m2 is equal to twice of m1. Substituting these values, we get Pd is equal to twice of m1 bracket starts twice of m1 divided by m1 plus 2m1 bracket closed whole square into u1 square whole divided by m1 u1 square, which on simplification gives me 8 divided by 9, which is equal to 0.89. Likewise, the value of Pc is equal to half of m2 v2 square divided by half of m1 u1 square, where m2 is equal to 12 times of m1. Substituting, we get Pc is equal to 12 m1 bracket starts 2m1 divided by m1 plus 12 m1 whole square into u1 square whole divided by m1 into u1 whole square. On simplification, we get 48 divided by 169, or Pc is equal to 0.28. So my values are 0.89 and 0.28, which matches with the second choice, and hence my second choice is the correct answer. Let's go to the next question. The density of a material in the shape of a cube is determined by measuring the three sides of the cube and its mass. If the relative error in the measurement of mass and the length are 1.5% and 1% respectively, then the maximum error in determination of the density is. Then the choices are 6%, 2.5%, 3.5% and 4.5%. Smile, it's a very simple question from error analysis. We know that the density of a material is equal to mass of the material divided by its volume. Now, since the volume is in the form of a cube, therefore density may be written as d is equal to m divided by a cube, where a is the length of each side of the cube. Or I can say that density d is equal to m divided by a cube. Taking logs on both sides, we get log of capital D is equal to log of m minus 3 times of log of a. Differentiating both sides, we get d capital D divided by capital D is equal to d small m divided by m minus 3 times of dA divided by a. Now, since errors never get subtracted, they only get added. Therefore, let's change the negative sign to the positive sign, and we get dd by d is equal to dm by m plus 3 times of dA divided by a. Or relative error in the measurement of density is equal to relative error in the measurement of mass plus 3 times the relative error in the measurement of length, or the percentage error in the measurement of density is equal to 1.5% plus 3 times of 1%, which is calculated to 4.5%, and my answer matches with choice number 4. The next question is 2 moles of an ideal monatomic gas occupies a volume V at 27 degrees Celsius. The gas expands adiabatically to a volume of 2V. Calculate the final temperature of the gas and the change in its internal energy. The choices are 195 kelvins and 2.7 kilojoules. The second choice is 189 Kelvin and 2.7 kilojoules. The third choice is 195 Kelvin and minus 2.7 kilojoule, and the fourth choice is 189 Kelvin and minus 2.7 kilojoule. It's a very simple question from thermodynamics. In this video, the blue color indicates a lower temperature, whereas the red color indicates a higher temperature. We know when a gas suffers an adiabatic compression, its temperature increases, whereas when it suffers an adiabatic expansion, its temperature decreases. For an adiabatic process, PV raised to power gamma is equal to constant, equation 1. And also for an ideal gas, PV is equal to nRT, or P is equal to nRT divided by V. Let us substitute the value of P in the first equation. We get T V raised to power gamma minus 1 is equal to constant, or T1 V1 raised to power gamma minus 1 is equal to T2 V2 raised to power gamma minus 1, or T2 is equal to T1 into V1 by V2 raised to power gamma minus 1. T1 is equal to 27 degrees centigrade or 300 kelvins, and for a monatomic gas, gamma is equal to 5 by 3. If we substitute the values, we get T2 is equal to 300 into 1 by 2 raised to power 2 by 3, which on calculation gives me 189 Kelvin. Now, the change in internal energy delta U is equal to N into F by 2 R delta T, where N is the number of moles of the gas and F is the degrees of freedom for the given gas, or delta U is equal to 2 into 3 divided by 2 into 8.314 into 189 minus 300, which gives me minus 2.7 kilojoules. So my answer is 189 Kelvin and minus 2.7 kilojoule, which matches with the fourth choice in the given question. Our next question: a solid sphere of radius r made of a soft material of bulk modulus K is surrounded by a liquid in a cylindrical container. A massless piston of area A floats on the surface of the liquid, covering the entire cross-section of the cylindrical container. When a mass m is placed on the surface of the piston to compress the liquid, the fractional decrement in the radius of the sphere dr by r is. My choices are mg by ka, ka by mg, ka by 3 mg, and mg divided by 3 ka. This is a very simple question from elasticity. For a solid sphere, we know volume V is equal to 4 by 3 pi r cube. Taking logs, we get natural log of V is equal to log of 4 by 3 pi plus 3 times of log of r. Differentiating, we get dV by V is equal to 3 times of dr by r. Now, the bulk modulus K is equal to minus of dP divided by dV by V. To understand the presence of the negative sign, let's watch the video clip. You can see for yourself that when the pressure increases, the volume decreases, and when the pressure decreases, the volume increases. Hence, the signs of dP and dV are opposite to each other. Therefore, to make the bulk modulus K positive, a negative sign has been introduced. K is equal to minus dP divided by 3 dr by r, where dP is equal to mg divided by a. Substituting, we get dr by r is equal to minus of mg divided by 3 Ka. We can see that neither of the four choices has a negative sign, because the question has asked the decrement, and the negative sign itself means the decrement in the radius. So very clearly we have to match only the magnitude of dr by r, which matches with the fourth choice in the given question. I hope you enjoyed this question. In case you have difficulties, please get back to me, and don't forget to subscribe this channel, and if you like the video, please like it and share it with your friends. Thanks once again, and do come back again for the next question.